Hi everyone. So in this video, we're going to continue to talk about differential equations, and specifically we're going to focus on how to solve one specific form of differential equation. So I want to just first start by reminding you from last time, what is a differential equation? So a differential equation is an equation. And specifically, it's an equation that relates or relating a function to its derivative or derivatives. And when I say derivatives, I mean, we saw in the last video that there could be the second derivative, for example. So an example of a differential equation that we saw in the last video was y prime is equal to 2 times y. So why is this? How does this kind of fit the description? Well, this is an equation, right? And it is a relationship between the derivative, right? So the derivative is y prime and the original function. And so that's y. And so specifically, this is a relationship that says that the derivative is 2 times the original function. So one thing that I hope that you got out of the last video, but I wish I had said a little bit more explicitly, is that a solution to a differential equation. So, what does a solution look like? Well, it's not just a number, right? So like you might think of solving an equation like, let's say x plus 1 is equal to 4. Your solution will be x is equal to 3. So in some equations, your solution is just a number. But when you're dealing with differential equations, your solution is going to be a function. And so in most of the examples we'll be doing in this video, it'll be a function y, which is a function of x. So, y is equal to something involving x. So it's a function that satisfies the equation. It's an equation or a function that if you were to plug it into the equation, you would get a true statement. So for example, we saw in the last video that the function y is equal to e to the 2x is a solution to the equation, the differential equation y prime is equal to 2 times y. Because if you take the derivative of y is equal to e to the 2x, you get 2 times e to the 2x. So you get 2 times your original function. All right, so there are lots and lots of different types of differential equations. As I mentioned, you can take entire courses, multiple entire courses about differential equations. In this class, we're going to be focusing just on one specific type of differential equation, which is called a separable differential equation. So in this class, I should say in this video, because we saw some other examples of differential equations in the last video. So in this video, we will be solving one type of, so this is sometimes used as a abbreviation for differential equations, called separable differential equations. So what makes a differential equation separable? Well, a differential equation is called separable if you can take it and rearrange it so that all of the x's are on one side and all of the y's are on the other side. So if it can be written in the form f of x dx is equal to g of y dy. And that might seem a little confusing. I'll show you exactly what I mean by that in a second. But the main thing I want you to notice about what I just wrote here is that basically f of x just means a function of x. So that means that anything that has an x in it is on the left-hand side. So you want to think of all the x's as being on this side, and then all the y. So g of y would be a function of y. So anything that has a y in it would be on the right-hand side. So let's see an example of a separable differential equation. So the equation dy dx is equal to x times y is separable. And so, by the way, you might notice this looks a little different from the differential equation at the top. You can either write a differential equation with dy dx, or you can write it with y prime, right? So this one had y prime. It means the same thing. And we'll see that if it's written like this one with y prime, you generally want to rewrite it as dy dx. So how can we see how this is separable? Well, if we start with dy dx is equal to x times y, and we multiply both sides by dx. So that's a really important thing we're going to be doing in this video. Basically, in all of these differential equations, we're going to be kind of separating out this dy dx. We're going to be treating it like a fraction and kind of taking the two pieces apart. So if we multiply both sides by dx, we get dy is equal to x times y times dx. And then how can you get the y to the other side? Well, you can divide by it, right? And so if we divide both sides by y, we can write that as 1 over y times dy is equal to x times dx. And so now we have, here is our function of y on the left-hand side. So all the y's are over here, and here's our function of x. And sorry, I wrote dy here. That was supposed to be a dx. Here's our function of x, and it's on the side with the dx. So what would a function look like that is, or an equation that's not separable? And by the way, we'll come back and actually solve this differential equation in a little bit. I just wanted to first kind of explain what I mean when I say separable. So the equation, so this is another one we saw with we did a slope field for dy dx is equal to x plus y. This is not separable. So we are not going to learn how to solve this equation in this class. We saw how to kind of get a rough idea of what the solutions look like using slope fields, but we're not actually going to learn how to solve this. So why is it not separable? Well, let's try to kind of repeat the process we did above. So if we multiply both sides by dx, the important thing to realize is that the entire right-hand side would be multiplied with dx. And so you might think, well, why can't we just like subtract the y over and then it will be gone? Well, because it's not just y on its own, it's y that's being multiplied with dx. And so if you want to subtract anything over or move anything around, you would have to distribute first. And so we would have x dx plus y dy. And so the issue is going to be that there's basically no way to get the y onto the other side without bringing this dx along with it. And so we're not ever going to be able to get it to look like the one above it. So it's not separable. Okay, so let's do some examples. So basically the rest of this video is going to be examples. I picked examples that I think each bring up something a little bit different, but I would definitely recommend after the first example or two, maybe try to pause the video and see if you can proceed with these examples yourself, and then kind of check in after you're done. So the first thing we want to do is we're going to solve the differential equation dy dx is equal to x squared over y squared. So first step is to separate it the same way that we did the example that we just did. So we're going to start by multiplying both sides by dx. That's kind of our first step in getting things, sorry, my screen is a little stuck. There we go. Getting things separated. So we get dy is equal to x squared over y squared dx. So we just multiply both sides by dx. And then how do we get the y squared onto the other side? Well, we can just multiply both sides by y squared. And so we get y squared dy is equal to x squared dx. So now what? Well, remember the goal is to solve this for y. And so we need to get rid of these dy and dx's. We want to, we want eventually to just have a function of x, right? We want to have like y is equal to something. And we really can't do that with this dy and this dx in there. And so what do? Well, we just integrate both sides, right? So if we take the integral of both sides, that will help us get rid of this dy and this dx. So what is our antiderivative on the left-hand side? Well, we would get y cubed over 3 plus, we can call it c1 because we're going to have a constant on the other side as well, and then x cubed over 3 plus c2. So I wrote a plus c on both sides, but it turns out you don't really have to, and from here on out, I'm not going to do that. So why do you not have to write a plus c on both sides? Well, remember that plus c is meant to represent any number, right? Any real number. So if I were to subtract this c to the other side, then together, these two would just give me a new constant, right? And because c2 and c1 both represent any number, if I group them together, that also represents any number. And so rather than go through this step of, writing the c on both sides and then subtracting it, you can basically just skip ahead and just assume that you've kind of put the constant on the side with the x. That's what I would recommend, is that because we're solving for y, it's generally just going to make things nicer to put it with the x. So we have x cubed over 3 plus c. Okay, so now we're trying to solve this for y, right? So we want to multiply both sides by 3. And so we get y cubed is equal to x cubed plus 3 times c. And so again, and this is going to kind of come up a lot actually in this section, when you have 3 times c, right? C again represents any real number. So if you have 3 times like any possible number, that's still just going to be any possible number, right? You can always get a number by doing 3 times something. And so we can take this constant 3 times c and we can just rename it. So if you want, you could rename it as just c again. It's a little funny, but I prefer to just give it a new name. So I'm just going to call it d. Okay, so now we're going to solve for y. And so we're going to take the cube root of both sides. And that's it. That is, now we have y as a function of x. And I'm not going to go through and do this, but if you wanted to, you could do what we did in the last video and actually verify this, right? If you were to take the derivative of this, you should be able to, it should satisfy this equation. So if you took the derivative of our answer and then put x squared in the top and then the original y, so what we found for y squared in the bottom, it would be kind of a complicated looking equation, but it should hold true. So this solution that we just found with the constant in it, this is what is called the general solution. So this is the general solution. It's kind of like when you're doing an indefinite integral and you have the plus c, right? You're saying there's many possible different antiderivatives and I want to kind of summarize all of them. And that's what this plus d accomplishes. So the next thing I want to do is actually find what's called a particular solution. So sometimes you're given a little extra piece of information that allows you to figure out what your constant is, and then you can come up with not just like a general solution, but one specific solution. One thing before I do that I just want to quickly mention that's really important, and this will come up throughout this video. Notice that the constant did not end up on the end. So we didn't just have a like little plus c at the end of our equation, right? It ended up inside of the cube root. So it's really, really important that you put the plus c at the right part of the problem. And so what I mean by that is, where does the plus c come from? It comes from integration. So when you do your integration step, so right here, when you write down your antiderivative, that's where the plus c has to first appear. And then if you just kind of keep going through the steps of the algebra and, maybe you'll end up renaming it something else, but the constant is going to end up somewhere inside of your function. It's generally not just going to be hanging out on the end. So I've seen a few students kind of make a mistake where they think they can just, not write the plus c and then just write it at the very end. And that's just not going to work because you need to know exactly where that plus c is going to be embedded within your function. Okay, so now we want to find the particular solution so I'm going to write something that maybe is unfamiliar notation, but I'll explain it in a second. If y of 0 is equal to 8, or sorry, y of 0 is equal to 2. So what is this y of 0 is equal to 2? It basically just means that if x is equal to 0, y is equal to 2. It's basically like forcing function notation into something that's not written in function notation. Right? So like, for example, if you have f of x is equal to x squared, you can say f of 1 is 1 squared, which is 1. If you have your equation written as y is equal to x squared, if you wanted to, you could say y of 1 is equal to 1 squared is equal to 1. So it's basically just a way of kind of forcing that function notation even when it's not there. So by the way, when you have this kind of extra piece of information, this is what's referred to as an initial condition. Okay, so how do we go about finding this? Well, basically this is telling us, we already know what our general solution is. And this is telling us that when x is equal to 0, y is supposed to equal to 2. So all we have to do is take this information and plug it into our general solution. So we get 2 is equal to the cube root of 0 cubed plus d. And so that means that 2 is equal to the cube root of d. And so if we cube root both sides, we find that 8 is equal to d. And so that tells us that our particular solution is y is equal to the cube root of x cubed plus 8. So I want to show you what this looks like graphically. So I'm just going to pull up Desmos here. So right now I have graphed our general solution. So x cubed plus d to the 1/3 cube root. So if I take this d value and I slide it around, we'll see that we can get different shapes of graphs, right? They're not all the same shape, they're different shapes. And so all these different graphs are sometimes referred to as the family of solutions to the differential equation because they're not the same function, but they are related. So they're a family. So you might remember from the last video that slope field idea. So remember the slope field, we talked about how there's all these different graphs that kind of fit within that slope field. And so it's the same kind of idea here. If we had drawn a slope field for this differential equation, we would see that all these different shapes can fit within that given kind of framework. So what did we find? We found that d was equal to 8. So if we set d equal to 8, now notice that this function passes through the point 0, 2, right, which was the piece of information we were given. So you can think of the initial condition as kind of pinning down your graph, right? You have all these different possible graphs, but as soon as you know one point that lies on your graph, then that kind of pins it down and can actually help you find the specific solution. Okay. So let's move on to another example. So next one we're going to do is actually the same one that we already separated at the beginning. So we're going to we're going to solve dy dx is equal to x times y, and we're going to have we're going to be finding a particular solution. And specifically, we want y of 0 to equal -5. Okay, so first thing we always do is find the general solution. You're never dealing with this information until the end. You're always first starting with general. So again, we separate this. We already did this one earlier, so I'll just do it quickly. We had dy is equal to xy dx. We divided both sides by y, and so that gave us 1 over y dy is equal to x dx. Okay, so what do we get what's our next step? We take the integral. Right, so we're going to integrate 1 over y and we're going to integrate x. And so the antiderivative on the left is ln of absolute value of y. And then on the right, it's x squared over 2. And again, we're just going to put the plus c on that right-hand side with the x. Okay, so the goal is to solve this for y. So we have to think about, what can we do that would undo this ln on the left-hand side? Well, the opposite of taking ln is doing e to a power. So what we want to do is actually exponentiate both sides. We're going to take e and raise it to the ln of absolute value of y on the left. And then on the right, we'll do e to the x squared over 2 plus c. So what happens on the left? Well, basically the e and the ln kind of cancel each other out. And so we're left with absolute value of y is equal to e to the x squared over 2 plus c. So to get rid of this absolute value, we have to introduce a plus or minus, right? Because if absolute value of y is equal to something, that means that y itself could either be positive or negative. So absolute value of y is equal to, just y is equal to plus or minus e to the x squared over 2 plus c. But there's actually a way we can kind of rewrite this that's a little nicer. So as it is, this is actually fine. It's technically correct. But we can basically take this c and kind of bring it out of the exponent. So how can we do that? Well, we can rewrite e to the x squared over 2 plus c as e to the x squared over 2 times e to the c, right? Because when you multiply two things together, you add the exponents. And so e to the c, well, that's a constant, right? That's itself a constant. And so we can rewrite this as y is equal to plus or minus, and then we can call this d e to the x squared over 2. But now we actually don't really need this plus or minus. So as it stands right now, because d came from e to the c, d actually represents a positive number. But we can kind of absorb this plus or minus into the d and just say, where d can be any number. So there's really no reason to have a plus or minus when you're multiplying with a constant, because the constant, we can just say, okay, well, maybe that constant's positive, maybe it's negative. We can kind of just absorb that plus or minus in. So the plus or minus can be absorbed into the constant. And I think this is kind of a tricky concept for a lot of students. And I really think it comes from the fact that you have to imagine when you have c or d or whatever it is, don't imagine it as being like one specific number. Imagine it as just this representative of any real number. And so if you have any real number, that number could be positive or negative. So you don't need to put a plus or minus. It's kind of already included by just putting a constant there. Okay, so this is our general solution. So now we need to find the particular solution. So the information we are given in this case is that y of 0 is equal to -5. So that's what we're going to be plugging in. So we want to plug in 0 for x and set it equal to -5 for y. So we have d times e to the 0 squared over 2. So what is 0 squared over 2? That's just 0, and e to the 0 is 1. So we have -5 is equal to d times 1, or just -5 is equal to d. And so therefore we can find our particular solution by just saying -5 times e to the x squared over 2. So one thing I just want to point out again is that that constant ended up in a totally different place than it did in the last example, right? In the last example, the constant ended up inside of a cube root. In this example, the constant ended up as a coefficient, and originally it was a part of an exponential. So it really, really depends on what type of function you have, where that constant exactly is going to end up. And as we mentioned, it's generally not just going to be tacked on the end. So let's take a look at this graph as well. So we have, here's the general dE to the x squared over 2. I don't know, oh, there it is, it's up there. So we see that, the graph changes for all these different values of d, but we found that d was equal to -5. And so if we put in -5, if I can get it to actually stop there, then we can see that the graph actually goes through the point 0, -5, which is what we wanted. So that helped us pin down that specific specific solution. Okay, so let's look at another example. So the next few examples are all going to be a little bit trickier. I think they're just going to kind of bring up slightly different issues. So this next example, I think the reason that this is going to be different is that it doesn't have any x's in it. And we'll see that that actually doesn't really mean much. It's really not going to change the way that we solve it, but it might seem different, at least at first, when you look at it. And I'm going to kind of phrase the initial condition a little bit differently. So let's say such that y passes through the point 0, 1. And that would be the same as saying y of 0 is equal to 1. I just wanted to kind of present it to you in a few different ways so that you can recognize it when you see it. Okay, one other thing that's different about this one is notice that it says y prime. So if you're given your differential equation with y prime, the first thing you have to do is rewrite it as dy dx, because you need those little pieces to separate and get your integrals set up. Oh, and sorry, I wrote this wrong. This is supposed to be 1 minus y squared. My bad. Okay, so let's start by separating this. So we're going to multiply both sides by dx. And then we can divide both sides by the square root of 1 minus y squared. But let's write that on the left-hand side as 1 over the square root of 1 minus y squared dy. And so on the right-hand side, we just have dx, right? And so that might seem a little funny, but remember when we integrate it, that's just going to be like integrating the number 1. So on the left-hand side, we're going to be integrating 1 over the square root of 1 minus y squared dy. And on the right-hand side, we're integrating 1 times dx. So on the left-hand side, what's the antiderivative of 1 over the square root of 1 minus y squared? It's inverse sine of y. And then on the right-hand side, we just get x plus c. Okay, so how do we solve this for y? Well, I would just think about, how can we rephrase this in a different way? So if inverse sine of y is equal to x plus c, that's the same thing as saying that sine of x plus c is equal to y, right? Because that's how the inverses work. And there's one kind of little extra thing we should put, which is that because of the restriction on inverse sine, the input in this sine function should be between negative pi over 2 and pi over 2. So x plus c should be between negative pi over 2 and pi over 2. So that's it. That's our general solution. So y is equal to sine of x plus c is our general solution. Okay, so now let's find the particular solution. So we know that this one goes through the point 0, 1. And so that means if we plug in 0 for x, we should get 1 for y. So we get 1 is equal to sine of 0 plus c. So 1 is equal to sine of c. So what is going to be the value of c that will give us 1 when we take sine of it? Well, pi over 2, right? Because sine of pi over 2 is equal to 1. Now, there are other angles such that sine is equal to 1, but remember that because of the restriction from inverse sine, x plus c is supposed to be between negative pi over 2 and pi over 2. So in this case, x is 0, and so 0 plus pi over 2 is less than or equal to pi over 2. Any other angle where sine is equal to 1 would fall outside of this range. So that's how we knew it was pi over 2 and not like 5 pi over 2, for example. So what is our particular solution? It's going to be y is equal to sine of x plus pi over 2. So this is our particular So this one, the graph isn't as interesting, but I'll just show you real quick. So we had here sine of x plus d, and the reason that it's not the full sine graph is because of that restriction on x plus d. So x plus d has to be between negative pi over 2 and pi over 2, so it's really just giving us this little snippet of the graph. So for this one, if I slide around the value of d, it's just going to move the graph. It's not really changing the shape of it. And so we found that d had to equal pi over 2, so that's approximately 1.5, and we can see that this graph looks like it goes about through 0, 1. So if we were exactly at pi over 2, we would definitely see it going through 0, 1. One other thing I just want to show you with this example that I think is kind of enlightening. So we found our solution, right? So we found that a general solution of y is equal to sine of x plus c, right? So let's actually check that that satisfies this equation, because I think it's kind of cool to see how it works out. So how would we check that this satisfies the differential equation? Well, we would take the derivative and then we would just kind of plug everything into this equation. So the derivative of sine of x plus c would be cosine of x plus c. And then what would we get if we kind of plug everything in? So we're supposed to have y prime is equal to the square root of 1 minus y squared. So let's kind of plug all of that in. So y prime is, we just found, cosine of x plus c. And we're checking, is that going to be equal to the square root of 1 minus y squared? So what is y? Well, y was sine, right? So we would have 1 minus sine squared of x plus c. And the left and the right hand side are equal, right? Because of the Pythagorean identity. So we would get cosine on the left hand side and we would get cosine on the right hand side because of that identity. So, maybe that kind of helps you see a little bit like why it is that 1 over the square root of 1 minus y squared. Why is the derivative of inverse sine? It basically comes from this Pythagorean identity. And this is actually something, if you go back to the Calc 1 videos, there's a video where we actually proved the derivative of inverse sine, and really the same kind of relationship comes up there. Okay, so we're going to look at a couple more examples. Okay, so next I want to solve. So the next couple we're going to look at are going to be ones where the separation is kind of the part that will make these a little trickier. So first one I want to look at is y prime is equal to e to the x plus y. So, first step we saw, and actually, sorry, let's add an initial condition to this. So we're going to have y of 0 is equal to negative 1. So first step is to rewrite this as dy dx, right? So that we can actually separate it. So at first glance, this doesn't really look like something we can separate, right? We have an x plus y, we're adding x plus y, which kind of might remind you of, this initial example here, right? We saw that this one here was not separable. But maybe let's actually look at the one above it. So if we can somehow get a product, then that will be separable, right? If you have a product of some function of x and some function of y, then you'll definitely be able to separate them because you can just divide by whatever the function of y is. So going back to this is something we actually already saw earlier in the video. We can split up this e to the x plus y. We can rewrite this as e to the x times e to the y. And now we can separate, right? Because now we can divide both sides by, or actually first let's multiply both sides by dx. But then we can divide both sides by e to the y. So we have 1 over e to the y dy is equal to e to the x dx. And so remember, we're going to be integrating both sides. So in order to find the antiderivative more easily, let's rewrite 1 over e to the y as just e to the negative y. And now we can take the integral of both sides. Okay, so what's the antiderivative on the left-hand side? Well, it's not just e to the negative y, it's negative e to the negative y. And you could do a substitution to find that, but again, that's kind of one of those substitutions that you might want to just do in your head. And what do we get on the right-hand side? We get e to the x plus c. Okay, so remember that we're trying to solve for y. So let's actually multiply both sides by -1 because that will make it a little easier for us to isolate y. So that would be e to the negative y is equal to negative e to the x. And then, we can call this minus c, or we can just kind of call it something else in the next step. So maybe the next step we can call this d instead of negative c. And so then how do you go about like isolating y? Well, we can take ln of both sides, right? ln, we already saw that kind of in the reverse direction. ln and e are kind of opposites of each other. So we can do ln of e to the negative y is equal to ln of negative e to the x plus d. And then on the left-hand side, the logarithm cancels itself out. So remember, ln of e to the negative y is basically asking you, what power do you need to raise e to get e to the negative y? And so the answer is negative y. The right hand, however, we actually cannot simplify. So, it looks like there should be something that can be simplified, but the problem is that logarithms cannot be broken up over addition, only over multiplication or division. So there's just no way to kind of separate out that constant. And without separating out the constant, there's no way to simplify the e to the x part. So we have to just leave that as it is. So finally, we want to solve for y. So let's multiply both sides again by -1. So we get y is equal to ln of negative e to the x plus d. And so this is our general solution. So now we want to figure out the particular solution. So the information that was given to us as our initial condition was that y of 0 is equal to -1. So that means that we should get -1 when we plug in 0 for x. So -1 is equal to negative ln of negative e to the 0 plus d. Lots of negative signs. And so that means that 1 is equal to ln of, so what's negative e to the 0? That's -1. Okay, so how do we solve this? Well, again, it's this game of kind of reversing, right, exponentiation and logarithms. So how can we solve this? We can just take, we can do e raised to both sides. Or another way of thinking about it is that it's kind of nice to just know ln of e is equal to 1, right? E is the only number that you can plug into ln and get 1. So that tells us that this whole thing has to be e. Alternatively, if you do, e to the 1 is equal to e to the ln of blah, 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 like you'll get the same answer. You'll get exactly what we just said, but I think it's easier to just kind of remember that fact. What can you plug into ln and you get 1? Well, e. And so that means that everything that's inside of this has to be e. And so that means that the solution here is going to be, so we have -1 plus d is equal to e. And so that means that d is equal to e plus 1. Oh, and that's not our final answer, sorry. So what's our final answer? Our final answer is y is equal to negative ln of negative e to the x plus e plus 1. Okay, so let's check out our graph. So that's this one, and this is supposed to have a negative sign. Let me just get that in there. Okay, so here's the general solution. So we see we have all these different graphs that look like this. And so we found that D was equal to, so E plus 1, so that's approximately 3.7. And so I'll just do that as an approximation, and we can see that it passes through 0, -1, which is what we wanted. Okay, one last example that in some ways is going to be kind of similar to the last one. And this one, let's just do a general solution. So let's just find the general solution to dy dx is equal to 2y minus 6xy. So again, this one at first might look like it's not separable, right? Because it looks like it's a sum or a difference of x and y. So we saw in the last example that if we can find a way to rewrite that right-hand side as a product, then we'll be able to separate it. Specifically, we want a product where the x's and the y's are kind of separated so that we can then divide out whatever needs to be divided. So how can we do that? Well, we can factor a 2y out from both of them. So we can rewrite this as dy dx is equal to 2 times y times 1 minus 3x. So now we can multiply both sides by dx and we'll be able to separate it. So, basically the bottom line is you don't give up immediately if you have a sum or difference. See if there's a way to rewrite that sum or difference as a product or a quotient where the y's and the x's are kind of separate from each other, then you'll be able to separate your differential equation. So here we get dy over 2y, or I'll rewrite that as 1 over 2y times dy is equal to 1 minus 3x dx. So we're going to integrate, and then in order to, you could just integrate 1 over 2y, but it's simpler if we rewrite it as 1/2 times 1 over y, because then we can just treat that 1/2 as a constant in our integral, and we can even pull it outside of the integral, right? So here we get the integral of 1 minus 3x dx. So on the left-hand side, we get 1/2 times ln of absolute value of y. And then on the right-hand side, we get x minus 3/2 x squared plus c. So let's multiply everything by 2, because we're trying to isolate this y. So we end up with 2x minus 3x squared plus 2c, but we can rename this 2c as d. So we have ln of absolute value of y is equal to 2x minus 3x squared plus d. And so now it's very similar to one of the ones we did earlier in the video. So you can exponentiate both sides. So we get e to the ln of absolute value of y is equal to e to the 2x minus 3x squared plus d. And so now we can separate, or we can simplify the left-hand side as absolute value of y is equal to all of this stuff. And that means that y is equal to plus or minus all of this. But eventually this plus or minus is going to go away because we can rewrite this as e to the 2x minus 3x squared times e to the d. And then we can rename e to the d. Let's not call it e because that's a little confusing. Maybe let's call it, I don't know, g. So that would give us y is equal to plus or minus, or let's call it f, I guess. I'm not crazy about f because that reminds me of a function, but let's just do that since it's the next letter. So we have f times e to the 2x minus 3x squared. And then as we saw in that previous example, we can absorb the plus or minus into that f. And so we'll just get f times e to the 2x minus 3x squared. And you could, if you wanted to, split up this exponent, but there's really not a good reason to. So, why do we split it up here? Well, it's because, I think for most people anyway, it's a little easier to understand a constant multiplied with an exponential function than having this kind of extra thing tagged on the end. And so it just kind of helps you write the function in a slightly more easily understandable way. So let's just look at the graph of this one. We only have the general solution for this one. So let me get rid of that one. So we can see that depending on what the value, I called it D here, but we called it F in the video, depending what that value is, you get all these different functions that are, look different from each other. All right, so that's it. And yeah, that's going to be it for differential equations. So this is really all we're doing is just these separable differential equations. And I think the challenge with them mostly just comes down to algebra and, especially kind of managing your constant and making sure that you're kind of doing the right thing with the constant and introducing it at the right part. All right, so I will see you all in the next video.